Hello and welcome to another tutorial. So this is the third part in the series of building our new behavior tree system. So previously what we have looked at is setting up some of the core interfaces, setting up things like our decorators and services, and also setting up our different nodes for controlling the flow through the behavior tree. So what we're going to be focusing on this time is getting the setup going for more of our action nodes, for things like the actual behavior tree, sort of, base classes, and the brain for a standalone behavior tree, and start getting things set up for being able to integrate this with our GOAP system. So that's what we're going to be looking at today. Now, if you're wanting to be following along with this, in the description below, you will find 3 links. The first is the link to the code as it currently stands at this point in the tutorial. The second link is to the code at the end of the tutorial. And the third link is to the completed package. So if you're just wanting to jump straight ahead to that completed version, then you're able to do that. And that full code is already available at this point in time. So no matter sort of when you're looking at this, that code will already be available there for you to access. So let's dive on in. So I said we want to focus this time on getting our actions set up, and in particular our action nodes. So we have previously set up our base action node, and that really was relatively simple. There wasn't sort of too much to that. We had some basic stuff for debugging. We had a helper for working with the return values. So we've got those bits up and running. What I want to get set up is the other sort of action nodes that I know I'm going to actually need, and a couple of just sort of common useful ones. So one of the common tasks I know I'm going to need to do is I'm going to need to be able to tell something to move. So I want to have a move action node. I also want to set up another common thing that we would want to be able to do is actually just wait for a certain amount of time. So we're going to have a wait node. The other thing that we do quite a bit of, and we do already have a service to do this, but we want to also have an action form of it, because depending upon what we're doing, we might want to use it more as an action form. So if we're doing a sequence of things, an action might be a better fit. So what this one does is this essentially figures out a suitable location on the nav mesh for moving to. So this is our calculate move location. So we're just going to get these 3 set up, and they're relatively straightforward. There's nothing too much to them. We'll get the wait one set up first. So this comes off of our action node base. We do our usual implementing of the default things. So our display name, we're going to follow the usual pattern that we have with all of them, where we'll provide a default at this point, like that. And then we'll set up a constructor that will allow us to override that. What I do want to do is, this won't be public, but we'll have a min time to wait. We'll have an optional max time to wait, because we might want it just to be a fixed amount, or we might want it to be random. So that's good. And we'll also keep track of the time remaining. So that looks like a pretty good setup. We'll set up our constructor, because that's an important part of what we need. So this needs to take in our min time to wait always. That's a mandatory thing we have to provide. but we will optionally allow the max time to wait. They'll default to null. Just make sure we get the naming of these consistent. And then similar to what we've done for a lot of our nodes, I want to make it possible to override the display name. So this is something that I've tried to do very consistently with all of these, because being able to override that name is actually really helpful to have. Lets people make it so that the debugging output is more useful, because if you've got a very complicated behavior tree, you could have dozens of wait nodes and dozens of things with the exact same name. Whereas if we allow that input, then I can customize it, and it could be, okay, wait for performing a particular action. We could provide context for what it's actually doing. And then we do our usual check for that, and setting our debug display name like that. So that's good. So pretty straightforward. Now what we want to do is we want to have our cooldown time, but I need to actually initialize that time remaining. So this is where one of the functions we can override is our onEnter, and that comes in really handy. So if our max time to wait is null, then it's very straightforward. Our time remaining is just our min time to wait. Otherwise, our time remaining, we actually can do a random roll. So we'll do a random range between min time to wait and our max time to wait, and we grab out its value. So yeah, this is having support for things like this and using a nullable type, so it's only optional for passing in that max time, allows us to create a node that, with minimal effort on our part, is able to function as both wait for a fixed amount of time or wait for a random amount of time between two values. So really useful to factor things like that in from the beginning. Now, in terms of what this needs to do for the actual ticking of the node logic, well, if our time remaining is greater than 0, then our time remaining gets reduced by delta time. Very standard logic. We then need to return our status. So this is where we can use our set status and calculate return value. Now, what our status is going to depend upon what our time remaining is. So if our time remaining is greater than 0, then our status is in progress. Otherwise, it's succeeded. So we'll just check this. So that's something where we need to go to our base here and modify this to give a default of null. That just means that it's going to not require that entry, so that's good. So that's all we need for our wait action node. That's all it needs to do. So let's get our move one set up next, because that's got a little bit more that it needs to do. Okay, so move one, its job is to, unsurprisingly, move the character to a particular location. So we'll get our defaults sort of implemented for this, do all of our usual logic that we would do here. Now, in terms of what this is needing to actually store, there's a few common things. So we've got our usual movement settings that we tend to need to keep track of things like our stopping distance. So how close do we need to be to our destination to consider that we've reached it? We want to have support for this being something that runs in a continuous mode. So that's particularly useful for if you are pursuing a target. this can be continually replanning. So that's good. We want to keep track of our last destination. And we want to have a float that keeps track of our recalculate threshold, and it is squared because we distance comparisons, if we can avoid it, we want to just be using the square of it. Lets us avoid having to do square root calculations, which are still something that is computationally expensive. So we want to keep track of that, so that's good. We have our usual setup that we're familiar with now in terms of our constructor. So we have our various parameters that come in. Stopping distance is the only one that I won't give a default for. The reason for that is stopping distance is a really important thing for taking into consideration. So by making it not optional, I'm kind of forcing that when you use this, you have to consider that stopping distance, because we do often want to use very different ones depending upon what the character is doing. If we're pursuing a target, our stopping distance probably needs to put us within at least sort of weapon range. If we are trying to just do a basic patrolling, we don't need to be that close, but if we're trying to interact with something, we possibly need to be super precisely positioned for the fact of then being able to play an animation for interacting with something. So I want to make sure that people are always considering the stopping distance, and that's why it doesn't get a default value. Continuous mode is something that I expect folks to need to use fairly often. So I'm going to not make it the default, but I will give it a default value. Then one to the recalculate threshold, and we get this passed in not as the square of it, but just as the actual amount, because it's easier from a working with a point of view externally to provide the true distance, and then internally we square it for use in our calculations. So that's one that I don't expect to need to be customizing much, but it just gives us a way of doing that if we need to. And our usual option for overriding the display name. So that's good. And unsurprisingly, setup stuff is exactly what we're used to. And recalculate threshold, make sure we remember to square it. If we forget, we're going to get some pretty odd behavior, so we do need to make sure we remember that. And then we check. That's not correct. Is null or empty, like that. And if it's not, then we just update our debug display name. So, okay, so far so good. So there's a couple of things that we need to be doing with this. We do need to hook into onEnter. The reason for that is because there's going to be initial setup stuff that we need to do. We also want to hook into onExit. And the reason we want to do that is because when we exit this note, we need to make sure that the pathfinding stops if it's gotten interrupted. So we're going to actually check here if owning tree, navigation interface, and if it is pathfinding or moving, we give it self, then we tell it to stop moving. The reason being, otherwise, it could just continue performing the moving, because the navigation system works in parallel with the behaviors. The behaviors send essentially directions or requests to it, but it is largely running on its own. So if it is still moving when we exit this, because we might get interrupted, we do want to make sure that we tell it to stop moving. So that is actually really important to make sure that we do that. Now, in terms of our onEnter, so the general logic that we follow with this is, okay, well, we need to attempt to retrieve our destination, but we're going to make sure we default that to an invalid value first. Then we will attempt to retrieve that particular value. So we're looking for our move to location. Oops, not constants. Names move to location. That gets output to our destination variable. And then we have a default of our invalid vector3 position. So if that has been successful, that means we have gotten the location back, which is good. Otherwise, we actually failed. So we want to indicate that we failed. Now, what we then need to do is that location, it might have read it, but that doesn't necessarily mean that it's actually valid. So we do want to check, okay, if destination is equal to that invalid position, then similarly, our last status is failed, and we actually do a return at this point. So this could happen if the location it's trying to find hasn't been set, which usually means that it's tried to move to a location that's off of the nav mesh. But that gives us our destination. So then at this point, we can assume that we actually have a destination. So we set that last destination variable we created to our destination, and then we attempt to tell the navigation system to actually start moving to that. So we need to give it self, the destination, and our stopping distance. Now, if that was successful, then our last status is in progress. So we haven't succeeded because we haven't determined that we've reached it yet, but we have successfully started things, and if so, then we return. I might actually move the setting of the last destination down into here, because we really are only actually using that if it has properly managed to set it. So that looks good for onEnter. Nothing really changes there depending upon whether we are in continuous mode or not. So our node tick logic is actually where we have most of what we need to implement. And a lot of it's going to be pretty similar to some of this. Because, okay, what we need to do is if we are in continuous mode, there's a couple of extra checks we need to do. So what I am going to do is, again, retrieve our destination, because that's actually really important. And I'm going to actually just bring down all of this logic because it's quite similar what we need to do initially. There'll be a couple of key differences, but it's largely the same. So yes, we do want to retrieve that destination. Now, if it has gotten back an invalid one, then this is where we use our return set status, and we pass in failed. That function just makes it a little bit cleaner and neater. So, okay, that's good. Now, we don't want to just immediately use that location because it might not have actually moved far enough. So the next thing we need to actually check is, okay, well, f our last destination minus this new one, and we get the square magnitude. Now, if that is greater than that recalculate thresholds squared. So we know that we've got a new point. So destination has moved far enough for a repath. If that is the case, then what we need to do is attempt to set the destination like this. So what we would then also do is a set status and of in progress. And we do the exact same logic here. Now, if this didn't succeed, if it knows that it needs to recalculate, but that location is no longer valid, we actually should fail at this point, because it's not managed to get a location that's correct. And it's not, it's managed to get a location, but it's not managed to actually set that for whatever reason. So we do want to properly handle that failure. So, okay, that's good. That's handling if it's in continuous mode. If it's not in continuous mode, or if it is, and it didn't meet, this criteria for recalculating, then we want to check. We might have actually reached the destination. We might still be moving. So first thing I'm going to check is, okay, are we still actually, pathfinding or moving? If we are, then it's straightforward. We return, we do our set status, and we are still in progress. So if it's pathfinding or moving, we always return back saying that we're in progress. Otherwise, we might have reached the destination. So if the owning tree in our navigation interface, and we check if it's reached the destination. Now what we return here is going to depend a little bit on if we are in continuous mode or not. Because if we're in continuous mode, then we've actually not ever going to come back with succeeded. So if it's continuous mode, I return in progress, otherwise I return succeeded. So continuous mode is never going to actually give you back succeeded. Continuous mode is one that is designed for you to interrupt it, for you to actually do a hard switch out of it. Otherwise, if none of those criteria are met, then that means we're not pathfinding or moving, we haven't reached the destination, so something has actually failed and interrupted the pathfinding. So in that case, what we should do is we should actually return back indicating that we have failed. So move does need to do quite a bit of logic in that regard, but it's really quite an important one for being able to, robustly handle all of that logic. So that's good. We've got wait up and running. We have move up and running. Now we can get our calculate move location going. Okay, so now for the calculate move location. So remember, its job is to essentially find a suitable location on the nav mesh for us to actually be moving to. So that move to Blackboard key that the move action uses, the calculate one, its job is to actually populate that. So that's really its primary purpose. So, okay, we do our usual setting up of things, calculate move location. We set up common variables that we're expecting to need. So we need our search range. This is one where we don't square it because we're actually passing it into something that needs the true distance, not the square of the distance. We want to have, to make this easy and reusable, we want a functor that what we do is it can take, it gives back a vector 3, and this is for getting our search location. This just allows us to reuse this action node for a lot of different purposes, whether it's a chase target, whether it is a wander location, whether it is something to interact with. Just allows us to substitute in a generic function there, which makes things much easier. Now this one, I want to support continuous mode for this as well. So we do already have a service version of this, but I wanted to set up a action node version of it as well, just because it actually is useful to have both, because our service can be really handy for us using in particular cases, but being able to do this as part of an action chain is useful. Having this be something that could work as part of a parallel node is also useful. So that's why I wanted to support continuous mode, just for those cases where we might need it. So handy to just have. So okay, we will have our recalculate threshold, and unsurprisingly this, because it's checks that we're doing on the distance of things, this we actually do store it as a squared one. And we have our last search location. So that's good. We'll set up our constructor. It's going to be pretty familiar structure at this point. So again, our search range is one that we don't want to have be optional. The same is true for our system.func for getting the search location. That's something that the function cannot operate without that, so we need to make it that it has to always be there. But everything else, we can make those optional. So continuous mode can default to false. Recalculate threshold also can have a default, and very familiar by now, our display name override also gets a default. So that's good. I would split these onto multiple lines, but the main reason they're appearing, covering this far, is actually down to me keeping this zoomed in so that the text is a bit more readable. So, okay, our usual logic that we're very familiar with by now. Search range is that. We populate our search location function, populate continuous mode. We've got that. Recalculate threshold, we just need to remember to make sure we square that. Yeah, and that's one of those ones that really easy to forget, and if we do, we get very broken behavior. It's doesn't break subtly, typically, so that's the one plus side with it, but it does cause breakages. So, okay, done our constructor logic. Well, on enter, unsurprisingly, we do want to override that, and there is logic we want to be doing here. So first thing we want to do is, okay, well, what if that get search location function is null? If it is, then we actually just fail out and return, because there is nothing we can do without that. That bit of information is something we absolutely have to have. So in our move location, we're going to attempt to retrieve that. So our vector3 move location, we execute our get search location function. Now, if that comes back as being our invalid position, then we need to also fail out. Because it's something where it just would make no sense for us to continue at that point. So, okay, if we get to this point, then we know that we've managed to run our get search location function, and it's given us back a location that in theory should be usable. But we need to check on the nav mesh for it. So we're going to find the nearest navigable point. So what we do for that is our move location becomes equal to, we get our navigation interface, find nearest navigable, give it ourself, the move location, and our search range. So that, there's a few things that could sort of happen with that. One of the things I do want to do initially is I want to immediately set that names and the move to location. So the reason I do this before I've even actually checked if that's valid is because if it's not, then we don't have a valid location to be moving to, and we should actually not just leave stale data essentially in the blackboard. So if we didn't do this, we would leave bad data in there, and that's not good practice. We want the data there to be good and reliable and be representative of stuff that can be used currently by behaviors. They shouldn't have to second guess whether it's valid data or not. So old data, we will end up, in this case, if the location's updated or has changed in any way and is now not valid, we'll mark that very clearly in the blackboard, which is good. So we then check again, okay, if that move location is invalid. And if that is the case, then not surprisingly, we fail out and return. Otherwise, our last status, if we are in continuous mode, then our status is in progress. Otherwise, we have succeeded. So this differs a little bit from our actual move, and the reason is that this just has a thing to do. Like once it's reached this function and has run that logic, its work is done. It only needs to stay around if it's in continuous mode. So that's why we've done this particular setup. So that's why in our on-tick node logic here, what we would do is our default is actually going to be to return that we failed, and our continuous mode is what we check here. So if we are in continuous mode, then there is actually logic that we can do. And what we would do is actually very similar to this. So I can actually bring this down here, because we do, again, want to retrieve that move location. Now, what I will do is if that failed, so if that got an invalid location, we should fail out. But if we've gotten that location, we need to check if it's actually moved far enough for us to redo the calculation. Because the calculation isn't cheap, so we don't want to redo it continually. So have we moved far enough to recalculate? So we know if we have, if we remember, we had our move location and we've got our last search location. So what I would be doing here is we want to check, okay, our last search location minus move location, if that square magnitude is greater than or equal to our recalculate threshold, then we can actually do this recalculation. So failure handling here will be the same. This then goes into here. So if it has successfully run, then okay, we know that if we get to this point here, we've recalculated and the new location is valid. So I'm going to set the last search location to move location. And I want to make sure that I'm doing this up here as well. So always important to make sure we're properly updating that. So, okay, we know that it's valid. And then otherwise, all we then do here is we would return set status, and it's just always going to be in progress. Because we're in continuous mode, again, similar to with the move logic one, we never actually will consider it succeeded. It's just going to always be running. So, okay, that's good. We've got those base versions of those different actions up and running. So that's a core chunk of our logic set up. We've got all of our base nodes, our base services, all of those sort of common ones that we are going to need to make use of. Now we've got some of the sort of fundamental wrapping infrastructure to set up, because these interfaces, most of these we've actually now implemented and got versions that we can start making use of. So the next things to get set up are for our behavior tree instance. So this is essentially the container for our behavior tree. So it will be made use of by our behavior tree based GOAP actions. It will also be made use of by our standalone behavior trees. So it's really important. We will also have a BT brain base. So our BT brain base, its purpose is it's used for when we have standalone behavior trees, so separate to the GOAP system. So these are the next priority for us getting set up. So we're going to work with the BT instance first. So it implements our AI behavior tree. That's sort of the core thing that it needs to do. It isn't based off of any existing class, anything like of that. We'll let it implement everything. This one is also not abstract. This one we typically don't expect things to be overriding it. So let's get a couple of these things populated now. So we have usual setup for our display name. So just populate that. So that's good. Our root node will be a get and protected set, but we won't initialize it at this point. Our blackboard is going to be the same navigation interface. It's also going to be the same. So that looks pretty good. Our adding the child to the root is going to be an important one. This is one actually that I can simplify that. Don't really need that node type there because it can just be an IBT node. So I'm going to modify that interface as well. That's good. Just simplifies the actual logic for it a little bit. So this is going to be very similar to when we were adding children to the other ones. We need to set the owning tree. We do a root node. We add that. So what we have to do is root node as a flow node, and we add child. So this is allowing for our root node being like of a selector or a sequence node. It wouldn't support if we had our root node being a parallel one, and that's okay. That's a limitation I think that is fine to support. That's good. We add the child. So all of that looks solid. Now it needs to then return that node. Just makes our logic a little bit easier. Actually, we can do the return as part of this. So that's good. So, okay, so far so good. That will allow us to add just those top level nodes to the tree. Now, in terms of then other bits, okay, our gathering of the debug data. Well, if it is selected, and this is something where at a later point we'll probably change that is selected to an enum that indicates verbosity. I can see that definitely being a thing that I'll change in the future, but for now we're just going to stick with the is selected option. So we'll do our debugger, we will add our text line, and this is our tree, debug display name. So not really much to it. We do want to, unsurprisingly, support having our gather debug data internal. So I'm going to set that up down here. Virtual void gather debug data internal. Taking in our game debugger and whether we are selected. That's good. So our BT instance has to implement that. And all I'm going to do for now is have this go and say root node, gather debug data, like that. So far so good. Reset, super easy. To our root node, reset. Tick, we just need to return root node dot tick. So those, quite straightforward. The actual BT instance here doesn't need to do a lot. It's pretty straightforward for its setup. Our initialize, well, we need to link up the blackboard. We need to link up the navigation interface. For the root node, I'm actually going to instantiate that here, and I'm going to explicitly instantiate a selector as that root node. So we'll give that the debug display name, and then we tell it the owning tree. So that's good. And we just do a check for when we grab that is null or empty. And that's actually grabbing the root node name like that, because that becomes our debug display name. So that's good. That's actually all this wrapper needs to do. Doesn't actually have to do anything else beyond that. So that's our behavior tree instance. Now the brain has to do a bit more. The brain is also, it is going to be a mono behavior. I will likely end up using a start and update, but for now I've removed them. So this is abstract. It is a mono behavior, but it will be a mono behavior that has to implement our IBT brain. I'm also going to get, actually no, I wouldn't put the add component menu for this one. That is something that we will end up doing though. So okay, it needs to keep track of our blackboard. So that's something where this is going to be a get, and I'll allow it to be a protected set. Like that, so that's good. So we need our blackboard. It is going to also have our behavior tree. So this is our linked behavior tree. and I will actually new that straight away, but I will make it a protected set and everything as well. So that's good. We've got our behavior tree set up. We will keep track of our navigation interface. That's good. We've got our nav interface. Our debug display name. We're actually going to make this just use the game object name. So I think that makes the most sense to have it tied to the name of the game object. And to make our life easier, we will have a public game object self. And actually that can just map to game object like that. Because self is a thing that we do tend to actually need to regularly sort of access, so handy to have that. So this is the brain for it, so it actually has to do a reasonable amount of logic. And if we go to our GOAP brain base, it's actually quite similar to, if we minimize our planning sections, it's got to do very similar to all of this. It has to actually populate all of these keys. So this is actually one of the things I'm going to do, is I'm going to take all of this and all of this populating of the inventory, configuring the blackboard. I'm going to delete all of the stuff for the actions, but the bulk of this I'm going to bring across. And that's because it actually is doing the exact same logic. So we're doing this in start. Now, something we could do is we could likely refactor some of this stuff so that we have sort of common logic for our brains. That is definitely a thing that we could do. We get rid of our binding of all of the actions. So far that's looking all good. There is unsurprisingly a lot of errors. That's what I would expect at the moment, because there is a lot of stuff we need to do. Our navigation interface, I'm actually going to do the retrieving of that earlier. So I'm going to retrieve that up towards the top, just because I think it makes more sense to make sure we've grabbed it as early as possible. Now, we have changed the name of the blackboard here, so I will actually change this one to match, so we've just got consistency between the brains. And I think that's something where it's going to be, I think later on I will be able to just set up a common, base brain that does a bunch of this stuff. So keeping the naming consistent between them now is going to make that refactoring safer and easier later. So we have our navigation interface, which again, I'm going to rename that just for the sake of making this that consistency. So that's actually good. So we've got our navigation. So less things are grumpy. There'll still be a few things. One of the things we have to do is our assembly definition for the behavior tree. We need to bring in our framework essentials. So that has to be brought in because that contains things like for our smart objects and our interactions. One of the other things that we need to bring across that's in our brain is, take a look, we've got this resource capacity. So we need to bring that over. So that resource capacity is for the gather behaviors. And at the moment, that needs to live on the brain. That is something that when I refactor stuff like the interaction systems and the inventory resource side of stuff, that is one of the things that I will end up refactoring out. So it's a steady process with this where I'll be refactoring different sections to adopt sort of that common approach of having things decoupled via interfaces, locating them asynchronously via the services. But for now, we just have to have that there. So that's good. We've got the populating of our inventory. We will definitely configure the blackboard and then have options for configuring the brain. What I want to do is the linked behavior tree. I want to initialize it at this point and link it to the blackboard and link it to our navigation system so that that's connected from the very beginning. So that's good. Oops, I've got the order of those around the wrong way. It's because there's so many errors at the moment, but that's okay. We'll have a lot less errors very soon. So we do want to initialize it. I want to have a helper for doing the configuring of the behavior tree. Like that. And the very first thing I'll do is once it's configured, I will actually reset the behavior tree, just so I know that it's in a clean state to begin with. So it's good. We have configuring the brain. So these are all going to become abstract functions or ones with partial implementations in a moment. So that looks good for all of those. We have our service location. We have our registering. So that's good. We're going to set up our onDestroy. The reason being is that we need to unregister from the debugger. So this is one of the changes with how the debugger now works, is that for accessing it, we have to do our async locating of it. But that's okay. So good so far. Our update. Well, our update is where what we would be doing is, and this is going to be, if we take a look at what this one does for update, first thing it does is set the position. So again, I'm going to do that because that makes the most sense. And I want to have that same sort of tick brain function. So that makes sense. Bring that over. That's good. So it is yet another function that we don't have implemented, so it's understandably grumpy, but that's okay. So gathering debuggable object content. If it is not selected, we're just going to bail out. Otherwise, we'll go for getting it from our blackboard. That, and then from our behavior tree. So most of these are pretty straightforward for what it's needing to do. We have our ticking of the brain, so that is going to be a little bit custom for what the behavior tree actually needs to do. But we do want to follow a similar logic to it. So this pattern of pre-ticking it, being able to have post-tick functions there, those are things we do want to actually replicate. So we're going to have protected, and we do want to not allow that to be overridden. So we'll have our tick brain, but delta time. So we'll do our pre-tick. Of our brain, that, and we'll have one post-tick. Now, in terms of what we do inside of that, well, we are going to run our behavior tree. So our linked behavior tree, we will tick that. And if the result was successful, so this follows similar logic to what we did for the GOAP side of things. If it was successful, I actually want to reset the behavior tree so it can essentially restart. But I want to call a function so that if there is specific stuff that we need to have happen, then we can actually do that. So on behavior tree completed, finished. And unsurprisingly, we do a similar thing for if the result was failed. But the difference here is we still do reset it. So resetting the behavior tree is something we still want to make sure we do. But what we run in terms of functions is our behavior tree completed, but we failed. So that's solid for our ticking logic. We want to get our reset system available. So our resetting of the behavior tree, it's pretty simple. We tell it that it's reset, but we do want to have a function that can be overridden just in case anything needs to do particular logic with that. And that's looking good so far. We do want to support, similar to what we had here for adding a child to the root, we want to make sure we support that as well. So that's something where I'm going to take, actually we can get rid of that. I'm going to take that particular one and bring that over. So our base brain is going to have this. That can be protected. So the reason it's protected is that these are designed for being inherited from and building it up via that inheritance approach. They're not designed for being an external thing. The behavior tree instance is something that we push changes into, but this is not. So that's the main reason why a lot of these things are being made. Actually, I might make that one protected. But that's the main reason why these ones are not being made public, is because they don't need to be. So except in specific cases like this, we're just keeping them public, or sorry, keeping them protected. Because this will then run our linked behavior tree like that. So that's good. And then we end up with a lot of abstract functions. So we have our abstract void configure blackboard. That allows an opportunity for whatever inherits from this to actually make use of any custom setup that it might want to do. We also have configure behavior tree. And finally, we have configure brain. So that's our three sort of configuration related ones. So now that we've got those ones set up, those ones I want to force child classes to have to implement them. Reason being is that I want people to make a conscious choice of what logic they're doing there. Then we have ones that are optional, because these don't need to be implemented for everything. So they are going to just have an empty implementation like that. So it's generally the approach I adopt is ones where it is going to be essential that a child class implements it. Either it's essential for functionality, or it's essential because I want anyone making use of it to have to think about what's actually happening. That's kind of the two cases. So even in ones where it's not essential for the running of the code for it to be implemented, if someone needs to consciously think about it, I'm inclined to make it abstract in those cases. So that is the scenario with these. Behavior tree, that one always is going to need to be implemented. Blackboard is a sometimes one. brain is even less rarely used. So they don't necessarily need to be implemented for things like of those, but I want people to consider it and think about it. And that's why I've gone for making them abstract. And then we have our pre and post tick ones for the brain. And I'm actually going to modify these so they take in the delta time. So I think that could be useful in some scenarios. So just to make sure we've got that available. So that's good. Delta times there. So let's see if this is grumpy at us, which it is, which is fine. So we just need to give those empty bodies like that. So we've got our instance that wraps around the behavior tree. We've got our brain base that is for our standalone behavior trees. And we've gotten our action nodes set up. So now what we can do is we can actually set up our support for the actual behavior tree based actions. So if we go to our GOAP system, so with our actions, we have our GOAP action FSM. I am going to create a GOAP action, and this is going to be our behavior tree one. So let's get that set up. So our GOAP action behavior tree serves the same purpose as our one for the finite state machines. It's basically a wrapper around those. So what we're going to do is this is an abstract class, and what it implements is GOAP action base. Get rid of start and update like that. And then we have a bunch of key things that it needs to store. So one of the things is it's going to need our behavior tree. Now you can see it's not managing to access it currently. And that's because what we have to do is in our hybrid GOAP, add in behavior tree, and remember to do apply like that. Now, if we get here and do iBehavior tree, it will properly auto-complete it. So this is our linked behavior tree, and we just initialize that to our new BT instance. So, okay, in terms of functionality that we need to set up, there is a bunch of things that we need to override. So our onInitialize, pretty important one to actually override. Our linked behavior tree, we need to initialize that. We need to give it our navigation interface and our blackboard. So those are essential. We're going to have a configure behavior tree function. So some of this is going to be similar to things that we set up in the brain. There is a bit of overlap between there. The action is a lot simpler. There's actually less that it needs to do. The reason being is that the brain has to, handle a lot more stuff that wraps around this for configuring blackboards and everything like of that. Whereas stuff like the actions just actually already have everything there. So we've got our configure behavior tree, so that's good. What we need to do is we also then need to, there's a few other ones to override. So our start action, pretty important one to actually override. So we're going to have a similar reset behavior tree function. And this is one where the resetting of the behavior tree actually is a thing that we will implement. So we will have a protected void, actually, well, yeah, that should be protected, void reset behavior tree. And that's going to do similar stuff to what we did with the brain, where we directly reset the behavior tree, and then we have a function that gets run saying that we reset it, but we will make that a protected virtual void, because we don't want to force that to have to actually be overridden. It's not one that everything needs to implement it. Okay, that's good. We've covered the starting of the action. We've got our resetting of the behavior tree there. We will set up overrides for a couple of other ones, just because we want to have, the reason for this is, although there's an empty implementation here, continue action is not something that every child is going to need to implement. And for the moment, we don't really make use of the continue action. It's more sort of some future support there. So I don't want to actually have to force everything to implement it. We'll have a similar thing for stop action. The difference is that our stop action actually can go and reset the behavior tree like that. So that's good so far. We will also have our overriding of the ticking of the action. So this is going to look fairly similar to what we did for the brain setup. So we get our result from ticking the linked behavior tree. If the result was that we finished, so if we succeeded, then we reset the behavior tree, and we're going to run that exact same function that we did previously, well, that we set up on the brain. So our on behavior tree completed and finished. So that becomes another one of these protected virtual ones. Unsurprisingly, we will also have a matching one for when it has failed. So on behavior tree completed and failed, because that gets linked up. Similarly here, if our result is that we actually failed, we again reset the behavior tree, and in this case we call that failed implementation one. So that's good. We've got our initialization, our start, stop, our ticking logic, all of those set up. We do want to add in a couple of sort of helper functions. We've already got the resetting. The gather debug data internal is one that we haven't overridden yet. So we override the gather debug data internal. With this, okay, what we're going to do is say, okay, if it is not selected, oops, then all we're going to do is exit out. Otherwise, our linked behavior tree, gather debug data like that. So for all the behavior tree ones, I've explicitly opted out of doing everything when it's not selected. Main reason for that versus the state machines is the behavior trees tend to be busier, so it means that there's a little bit less stuff there. But again, this is something that in future I expect to change that over to an enum that's indicating the verbosity of what we're doing. And then the final thing I want to add in is the same thing that we've got in all of these base brain ones and everything, this adding the child to the root, because that is something that every one of the actions is going to need to be able to do. So that looks good. That gives us a base version of our actions there. And what I will do, just as a sort of finishing up of this, is we're going to set up a single one of our common actions. So I'm going to create a folder here for BT common. So we're going to set up what one of these behavior tree based actions looks like. And we're going to go for a fairly straightforward one. So what this will be is this will be our GOAP BT action. And we'll go for the idle one to start with, because that's a pretty straightforward one. So this is going to need a couple of things once it decides to load. So this, we've already got our state machine based implementation of this. This is going to be our behavior tree based implementation of it. So what we need to do is, first thing, we want to have an add component menu. And we just set up a path for this. This is BT action and idle. This is based off of our GOAP action behavior tree. We don't need start or update. We can tell it to do the implementations. So we know we'll need some settings here. We'll know we'll need a min wait time, which will default to 1. We know we'll need a max wait time, which I'll actually default that to 10. So calculating the cost, I want to have the cost for this be super cheap. So we return 0. Configuring the behavior tree, we will get to in a moment. In terms of resources, we would be using the legs, and we would be using the torso. The supported goal types is going to be a new system type array that just contains a type of GOAP goal idle, like that. So then all we need to set up is the actual behavior tree itself. So how I would go about this is I would go for setting up a variable that's just a local root. We do an add child to root node. We're adding a new flow node selector. I like to just group everything under a selector generally as sort of the top level thing. So this, and I want to cast it to our flow node selector. And then all I need to do is local root, add child, and a new BT action wait. And I give it the min wait time and the max wait time. And we're done. That's all it needs to actually do. And if we compare that to our SM action for idle, largely very similar. Has the same parameters exposed, cost and everything. Here we did a little bit of stuff to filter out what we needed to do for the transitions, but all pretty straightforward with setting this up. So that's good. We've got our idle action up and running there. There are other ones that we could get set up, but we're going to take a look at those next time. So we're very close to being in a position where we're going to be able to actually see these things running and be able to properly test them. Again, this is a lot of infrastructure that we have to build up to be able to test it. That is unfortunately the nature of when you're building a fairly complicated system like this. To really be able to properly exercise it, you need to actually get fairly solid amount of stuff implemented. But now that we do, we've got a lot of pieces that we can start making use of and start putting together, and then that's going to make things a lot easier. So next time we will actually be able to see some of these behaviors running. We'll be able to see them for the actual GOAP-based version of running this, and see what that same version would look like as a standalone behavior tree. So we'll look at both of those in parallel. So folks, hope you found the video interesting and helpful. If you have, chuck in a like and subscribe. It really helps out. It's really appreciated. Now, if you're looking for the code, there are 3 links in the description below. The first is to the code as it was at the beginning of this tutorial video. The second is a link to the code as it currently is at this point in the tutorial. And the third is a link to the completed package. So the full set of all of the code is available up there, and that's, even if you're watching this just as it's come out, the full code is already available there if you're wanting to check out later sections of it. But dive on in and experiment with that. If you've got any questions, chuck those in a comment below. That code, as always, you can be making use of that in any of your own projects, commercial and non-commercial ones. There's no charge there at all. And if you are looking for other ways to support the channel, then I do have a Patreon, and there is a link to that in the description as well. But until next time,